We are almost ready to start. I suspect someone will join later on, but I don't want to wait too much to start with the program. Otherwise, we are going long. Session this morning will be managed by Domenico Siracusa, that will introduce all the speakers that are in the agenda. Please, Domenico.
So, good morning, everybody. I'm Domenico Siracusa from Creanet, and I'm happy to chair this session of the morning, which is the ONOS activities in EU, related with activities from the different universities and also the GEAN project that we have over ONOS. I was kindly appointed yesterday night on doing this, so I'm quite happy to support and to thank the organizers, and on behalf of Creanet, the organizers team and all of this workshop. So just a logistic note, everybody has to use the microphone for questions, this one, the mobile one, or you use the mic on the bench here. When we have questions, we will go around with the mic. Mario is already provided one. So we will give the audience the possibility to make a question. So the first presentation of the morning is from Abubakar from Politecnico di Torino. He will present us intercontroller traffic in ONOS clusters. So let me welcome Abubakar.
Okay. Good morning, everyone. My name is Abubakar Siddiq, and I'm a PhD student here at Politecnico di Torino. And the topic of my presentation is intercontroller traffic in ONOS clusters for SD networks. So without further ado, I'll start. The notion of distributed controllers in SDN is motivated by mechanism and its resilience, and it also provides redundancy in the form of master and slave controllers. So having multiple controllers actually balances the load of the network. So you may have higher scalability for larger networks. But the critical issue remains is how do you distribute the network state across the controllers so that the controllers agree on the network state to allow a logically centralized view. Controllers, the control plane consists of two types of traffic. The first is the typical switch to controller traffic at the southbound level, which consists of the standard southbound protocols like OpenFlow. And then you have the traffic which is exchanged among the controllers, the intercontroller traffic. This intercontroller traffic consists of some ad hoc protocols in the east-west interface, which are needed to coordinate them about the state of the network. These carry the consistency protocol related information. See here means that the controllers agree on the state of the network. This may require sharing some distributed data structures, the controllers, and there are different models to do that. So assume you have a shared table with a key value mechanism. So a strongly consistent data structure always returns the same value whenever you read from it. But in an eventual consistent data structure, there may come a time where you don't have the same value, but eventually it returns the same value. So you may have a different value for some transient time. Now, coming back to ONOS. ONOS consists of some distributed data stores. I've mentioned some of them. One is the network topology store, which describes the network topology in terms of the links and switches. Then you have the mastership store, which actually saves the mapping from the switch to its master controller. Then you have the flow store, which maintains the flow tables of the switches. A host store, which maintains the list of hosts in the network. Then you have an application store to manage the inventory of applications, as well as a security related store. And these are all distributed and synchronized among the controllers. So the interesting ones that we focus on in our work are the network topology, the flows, and the hosts, because the others are more related and dependent on the type of application that you're using and the network level dynamics. So our contribution consists of devising an experimental model using ONOS as the controller to evaluate the required bandwidth which is needed for the intercontroller traffic based on the contribution of the network topology, the flows in the network, as well as the hosts. So using this model, it's very useful to design and dimension the transport network which carries the control plane traffic. But in our work, we neglect the switch to controller traffic at the southbound level because it can be independently computed based on whatever network application you have and whatever flow dynamics and whatever protocol in the southbound that you are using. ONOS also has employed the consistency models for eventual and strong consistency. The eventual consistency part of ONOS is managed by an anti-entropy protocol, and this manages the network topology, the flow rules, and the flow statistics. The strong consistency part is managed by a raft consensus protocol. This manages the switch to controller mapping, some distributed logs for a distributed operation, as well as the hosts in the network. So in the anti-entropy protocol, the updates are local for the primary controller, but they propagate in the background with Gaussian algorithms to synchronize other controllers. So every 5 seconds, each controller picks at random another controller. They exchange the replicas of the data stores and they reconcile differences based on timestamps if there is any change. The updates are centralized to a leader. So it's a leader follower mechanism. And whenever there is an update in the network, it is always the leader is always responsible to commit this throughout the network whenever a majority of controller acts to the leader. So coming to the contribution of the network topology store to the intercontroller traffic. This is managed by an eventually consistent anti-entropy protocol, and it's a periodic traffic exchange among the controllers. So we utilized Mininet to emulate any arbitrary network topology having arbitrary number of switches and links and divided among the controller domains. Then we use Linux containers for the ONOS instance. We used ONOS 1.4, which was released in February. And we utilize a traffic sniffer to evaluate the intercontroller traffic. Then we have these two scenarios for the 2 and the 3 controller that we utilized in our work. And the controllers are always connected in full mesh to each other. So the model for the intercontroller traffic based on the topology takes as an input the network topology and how the switches are divided across the domains of the controllers. This consists of the number of switches, the number of intra-domain links which are within the domain of a controller, then some inter-domain links for the links which are divided across the controllers. And as an output, we use the empirical formulas which we derived experimentally for the intercontroller traffic bandwidth. These switches and links as input and give the output as a form of bandwidth amount of traffic which is required to exchange among the controllers. This is a scenario with 2 controllers where we connected a linear topology to controller A, and these are the graphs which denote the bandwidth required for the against the number of switches for a linear topology. On the left you have from controller A to B, and on the right from B to A, and the switches are added to the controller A. Linear trend with the increasing number of switches against the bandwidth. And the reason why the left graph has more like traffic as compared to the right one is because the switches are added to controller A and the switches are managed by the master, which is the controller A. So we derived the empirical model for 2 and 3 controllers. So this is the 3 controller scenario in which we have 6 possible values of bandwidth which are exchanged among the controllers. On the left, the upper part of the table, you have the inputs for the formulas, the number of switches and the number of links, number of intra-domain as well as the inter-domain links, which you can plug into the formulas in the right, which we derived, which are empirical formulas, which we derived experimentally. And you can get the bandwidth which is needed to exchange among the controllers. Okay, so the next one is the flow store, and we studied how the flows actually impact the traffic which is exchanged among the controllers. So in SDN, each switch is typically associated to a master controller, and you have some optional slave controllers. And in ONOS, a copy of the switch flow table is maintained at the current master controller, as well also the next potential slave controller. there's a function which is running in every master controller that if there is any change in the flow, this triggers a backup of the entire flow table from the master to the slave via intercontroller traffic. So even if there is one change, all of the flows are exchanged from the master to the slave. We utilize this methodology to observe how the flows are carried out, the backup. So we installed flows on the controllers using the REST API, and then the controller installs it on the switch, as well as backs them up to the slave controller. And then we use the sniffer to observe the packets which carry flows on the intercontroller traffic. And using these packets, we can infer how much bandwidth is carried per flow. Almost two flavors of OpenFlow, 1 and 1.3 are utilized. And for example, in OpenFlow 1.0, the match bits are roughly 240 bits. But as OpenFlow evolved, it has increased up to 548 bits, excluding the table part. So the experimental results, we observed that on the intercontroller traffic, OpenFlow 1.0 flows, for these exact flows, we found out around 304 bytes per installed flow for OpenFlow 1.0. And for OpenFlow 1.3, this is around 409 bytes. So considering commercial OpenFlow switches, they may have a capacity of thousands of flows. Even one change in the flow table, and let's say all of these match and action fields are utilized, you may have in the worst case megabytes of data which may be exchanged among the controllers and every 2 seconds. So this is a huge amount of data, and it needs to be like researched upon. So now coming to the hosts are managed by a strongly consistent raft protocol. It's the raft is a consensus protocol which is used for strongly consistent guarantees. And in raft, as I mentioned earlier, the updates are centralized to the leader, and the updates are incremental. So if there is any change in the network hosts, the updates are exchanged once, and once they are committed by all the leaders, you don't need to exchange anymore. So it's not periodic. The methodology is that the same we utilize for the flows. We inject hosts into a controller via REST API. And you may have two scenarios in this case. For example, using 3 controllers, either the hosts are added to the leader controller or the hosts may be added to the follower controller. So if the hosts are added to the leader controller, the leader just starts the synchronization round, sending the updates to the followers and getting an acknowledgement, and then committing the host to the distributed data stores. But in the case when the hosts are added to the follower first needs to update this information to the leader, and then the leader will start the consensus round among the controllers. So you may observe a little more traffic on the case that is on the right to the follower. So for example, for the 3 controller case, when the hosts are added to a follower, the traffic that is exchanged among the controllers per host in the case of leader to the follower one to which the hosts were added is around 2000 bytes per host. And for the leader to the follower 2 is a little less than that. And 2000 bytes are very significant if you have a lot of hosts in the network, especially if you have a mobile network. So concluding my presentation, I would like to summarize all of the contributions that we had. So we experimentally evaluated the intercontroller traffic in terms of bandwidth for the ONOS SDN clusters. Here I'd like to mention that this is independent of the network load in the southbound in the data plane. So for the network topology store, if we add the topology to the controllers, it increases at most around bits per second for each network element, either switch or link. For the flow store, based on the OpenFlow version, it's around 300 to 400 bytes, which are exchanged per installed flow. And for the host store, almost 2000 bytes. So these numbers actually highlight some possible scalability issues due to the intercontroller traffic. And these numbers are quite large. And this indicates that the control plane should be carefully designed and dimensioned before it is deployed. Just on the last note that my research group also tackles the problem of the controller placement. So in a large network, it's very important. You need to know where to put the controller because it affects the performance. So if anybody is interested on that, they can ask me as well. I'll forward it to the appropriate person. Thank you. Any questions?
The question may be that if you made in your PhD thesis any theoretical investigation about the impact on the architecture of the intercontroller domain due to the statement of the Beaver theorem, which is a theoretical that asks you to make some trade-off between three parameters, main parameters.
Yeah.
Which are partition tolerance, availability, and I forgot the last one.
Yeah.
Thank you.
It's really important because it depends which kind of consistency model you are using. It's the CAP theorem actually. So either you are focusing on consistent, want more consistency, more availability, more partition tolerance. So what I worked on the traffic. So if you change the model, obviously your traffic will change. You're more interested in a strongly consistent part, so you will have more traffic related to that strongly consistent. Either it may be incremental or it's periodic, that's another question. So it really depends what kind of model you want to use. They also utilize the eventual consistency. So it's periodic as well, but then there is raft as well. So it depends what kind of application that you're targeting or what part of the network you're targeting.
Just a question. I think that you have OpenFlow as protocol. So essentially, most of the exchanges are due to the exchange of forward link.
Yeah.
Suppose you don't use OpenFlow.
Yeah.
You have controllers, and the type of protocols does not imply a large exchange of rules.
Okay.
How the picture you presented us will change?
Just I'd like to mention again that in ONOS, for example, if there is only one change in the flow table, the whole flow table is carried out. So the flow tables can be large as well. But if it is a different protocol, I'll need to revise these numbers, obviously. So if it's netcon for some other southbound protocol, I'll need to revise these numbers appropriately. But this just highlights that there is this possible scalability issue.
Any other question? If not, we should thank the speaker.
Thank you.
Can you open this one? Ok, no. Ok. Sei tu il primo speaker. Ok. So the next talk is from Jean, the Jean Testbed Service, GTS with ONOS and CORD. This presentation will be given by Fabio Farina from GAR and Michael Azinski from Chestnut. I don't know who's starting. Fabio. Fabio, okay.
That's me. Good morning.
You need this one?
That's the remote control. Okay, here.
Yeah,
Okay.
fine.
Try to move a bit forward so you can see me. So today we will give a brief introduction to GTS rather than going into deep because we are not familiar enough to draw a neat future with these tools. But for sure, we have great experience. We have had a great experience in supporting ONOS, and we will tell you this experience at the roadmap we fostered thanks to this. So why GTS? Stands for Giant Testbed Service. The idea behind the service is that when you are innovating in networking, simulation and emulation are the coolest tool you could use, but they have a very little defect. They clash against reality. So you need testbed, you need a real network, you need near real context to crash your algorithms, your tools in work. On the other hand, testbeds are complex, are focused on certain technologies. And so we wanted to design something more than just a testbed. We wanted to design and realize a testbed factory, something that allows you to create a new testbed in a user-oriented way, feature-rich, user-friendly with an agile approach in mind. With agile, I mean rapid prototyping. You can destroy and recreate in horizon, and you can do disruptive experimentation too without interference with other users' tested. As I said, work with testbeds is really complex, and it could jeopardize having a new testbed for every kind of new experiment your work. So the idea of GTS is to provide to research community a general tool, open access tool that you can use for your experimentation. And this is the use case that Jerry designed years ago, and we are using still this nice presentation. So you have about networking. You log in into GTS GUI. It as a generalized virtualization model graph. And GTS, through its life cycle, converts it in some different representation that gets mapped on the actual resources. Then you activate your resources, you do your iteration, iterate again and again according to your needs. To go more in detail on the generalized virtualization model, everything in GTS is represented as a data flow graph. Just the classical graph you think about when talking about a network with host link switches. But GTS considers this actually as a bipartite graph. Resource is equipped with a couple of ports, and you create relations using the adjacency concept. So a link between two virtual machines is made of two hosts, one link for the host and the link, and then you connect these entities at a single structure. Of course, this sounds a bit complex, a bit verbose, but here I'll explain a bit later how this has been made extremely simple and effective in GTS. This is a taxonomy, a very brief taxonomy of the resources that are currently available in GTS. And we can cluster the resources in two kinds: atomic resources that are host virtual switches. Currently, we are supporting open flow fabrics through OVS, but Michal will explain how we are evolving on this. We support Ethernet over MPLS links, both port-based and VLAN-based, and in particular, we support external domains. And so GTS has the capability of extending beyond its borders. So it can reach up to your laboratories if you need to span across. And of course, we have internet access gateways to let you access your testbeds, install packages, and things like that. And the composite are aggregates of atomic resources, or recursively, composites can be made of other composites. How GTS interacts with the user. If you use to operate with SFA-based testbeds, for example, you know that you have to write tons of XML configurations to describe your request. We decided to start from a thing isolated, and what we did is we started from Java, from a Java dialect, Groovy. This way, every student, every undergrad student is able to describe easily its own testbed. And furthermore, we inherit a lot of feature-rich capabilities like iterators, like object-oriented approach. So you could describe hundreds of resources with just a for loop, or you could have a template made as a class and instantiate that class in many different fashions to the constructor. This is just an example. I won't go into detail with that nasty code. So as I said, when you start from a virtualization layer, you describe through your DSL a resource, but then you can compose the resources in a hierarchical way. So your testbed could start and just working on the language get larger and larger. So now I leave the stage to Michal for more details about the infrastructure part.
Okay.
Okay, yes.
Okay. Okay, hello. Fabio just described abstraction of the resources, and I will add a few sentences about how resources are actually done down there in the physical infrastructure. For GTS was at the very beginning isolation of physical part of the infrastructure belonging to different projects, different users. They must not interact between each other, and also it has to be safe when some testbed failed because of it must not have some influence on some other testbed which need to work as usual without any interaction. So we designed everything very carefully, and as Fabio showed, those resource classes. And for example, if you have a resource class in which is, for example, host, the VM, down there in the infrastructure, it's a VM on the KVM server managed by OpenStack, and GTS just asking OpenStack for just one VM. On the networking level, it is quite isolated. We didn't want to manage network by OpenStack and develop our own algorithm and RCAs, which directly structure and configure everything on the physical interfaces and stitch it to the VMs, and they are not involving each other, and it works quite well. I mentioned RCA. It's a agent, software agent in the generalized virtualization model, which cares about different class of resource. It's our RCA, and this RCA is responsible for managing the part of the infrastructure where resources are instantiated. So we have RCA for communication with OpenStack, RCA for OpenFlow fabrics. This one is interesting, I think, for this forum, and I will mention this later. Also, we have RCA for VCs, virtual circuits. It's basically Ethernet over MPLS, and it's handled by NSI, so it supports multi-domain links. And we have also other things. I will pass forward. This is what is currently out there. We have 9 locations across Europe as giant. Locations are depicted there. There are about 36 bare metal servers currently work as compute nodes for OpenStack. We have physical OpenFlow fabric in each location. Currently, it's HP 5900, and we have switch router with MPLS backbone between locations. We provision our own MPLS cloud and doing traffic engineering for VCs. Links between locations are currently 10 gigs. We tried to maintain full mesh between locations at the beginning, but we need to leave it. And currently we try to maintain hypercube between locations. Full mesh was we just had not enough ports in locations for maintain full mesh when we scale up. There are also deployments in some partner NRANs. You can see that there are one node currently in last phase of development in VNet. We have 2 function nodes in CESNet in Czech Republic. And there are 4 in NordNet, and there are some also coming up in DFN. Okay, I will leave stage to Fabio because he works with users and he can tell you some use cases.
Sorry about the users that use GTS so far. Last Tuesday, we had about under 50 resources allocated with about 70 circuits over 22 projects, but this year we had more than 30 projects active in addition to the 22 that are currently running. The largest project we hosted is the ONOS project in the Università di Roma that involves more than 30 resources. We are particularly proud of having many grad and undergrad students in their activities. We are in contact, we are in strong collaboration with Fed for Fire activities and in particular with iMind. They developed a JFED GUI extension, for supporting also GTS that are more familiar with drag and drop interfaces rather than coding can use this tool to deploy their testbed. Bringing in users like LHC1 that is going to experiment the SDX fabric concept for their needs through GTS. LHC1 is the one of the networks that the CERN experiment transfer data across the data centers worldwide. From my side, I'm going to give. Oh yes, this is the most important one, man. This is the detail about the ONOS testbed. The testbed is a huge testbed across many different countries, and a relevant part has been hosted by GTS. And I cannot see that if that part is very readable. By the way, the testbed has been shown initially in London, and then it ran for quite a long period from June to September, and we had one more demo at ONS 2016, where the global ONOS testbed has been shown. More detail about the portion of the testbed hosted on GTS. As I said, many resources. You can see from the screenshot the list of the resources. The testbed was quite spread across the DGTS POPs. They involved a classical cluster made of 3 nodes over 3 distant 3 BGP peers to enact IP. I cannot remember the IP SDN IP. Sorry. Plus additional service for doing persona is a monitoring tool for assessing performance. One part is that the testbed used strongly the external domain ports to reach also the US. The very first usage we did for this kind of extra domain, inter-domain stitching for testbeds.
Sorry for my lack of knowledge. Can you explain shortly what is Internet 2?
Oh yeah, Internet 2 is one of the research and education networks in the US.
An overlay?
No. It's a backbone for university and research centers in the US. In Europe, we have DART in Italy. We have DFN in Germany, and research networks.
Okay, and I will try to add some more information about where we are heading and what is on our roadmap. We had a few GTS technological and features workshops and getting feedback from the users, and based on that feedback, we are still evolving and working on new features. By the way, there is one workshop upcoming. It should be February 2017. Just watch our website or stay in contact with us if you are interested. We can let you know sooner. Okay, what is currently on our roadmap? We are preparing bare metal server as a resource, so you can reserve a physical server for your own and connect it into your network topology. So you will have access to quite strong powerful compute component. The original idea of the resource is performance measuring. So that's one resource some of our users waiting for currently, and it's coming this fall. We are migrating to 10 gig users links. Currently, we have 10 gig backbone between locations, but every resource are interconnected only by 1 gig. As it was at the very beginning, basically as a proof of concept, but it stayed there. And currently we are upgrading for 10 gig, and we are going to interconnect everything on 10 gig, so user will have the opportunity to reserve all 10 gig between their resources if needed. Fully virtualized switching fabric. That's something interesting for OpenFlow experiments. At the very beginning, we tried to somehow share switching fabric between users, because when we have 48 port switch and just one project or one user will reserve it, there will be nothing for others. Okay, I am mentioned that I need to speed it up, so I will skip this. Basically, what is important for you that is we defined OFX as a resource class. That means virtual OpenFlow switch, but it is not virtual. We have hardware implementation. You have full line rate for hardware performance of the switch. Currently, it's implemented on the HP 5900, as I said, and we have implementation for new white boxes from Corsa. Corsa supported fully all our defined features for the virtualization. You can instantiate just a switching instance inside the white box, reserve just, let's say, 4 ports for the switching instance, and another project can reserve another instance, have another 4 ports, Again, line rate. And since there is a backplane capacity in the switch, users can share the line rate, which is quite, I think, quite interesting. And also we are supporting virtualization on ports, so you can define your virtual port on the tuple port VLAN, and you can have relative names on ports. So you can name, for example, port 10 VLAN 300 on the physical interface, and you can, for your virtual instance, you can name it as port 1. And you will see on your packet in port 1. So it's completely relative for your virtual topology. Here in the left is an example what all can be set through our DSL and will be instantiated on the physical switch. If you want more information about it, please find me somewhere else. I need to end because I'm over my time slot. Thanks.
I would like to have a final remark, just 1 minute. Yesterday, often we talked about the chance of contributing to ONOS, for example. I want to stress that GTS is open access. So we have HP, we will have Corsa very soon, we have OpenFlow. I invite you just to register and to start working with ONOS, maybe CORD, and your technology since today. So it's open, use it. Thank you.
To thank the speakers for the nice presentation and the final invitation, which everybody is suggests to take. If there is any question from the audience, I have a quick one. So I see you're basically virtualizing resources, but are basically mostly packet resources. Like the optical equipment, for instance, or is it not in the roadmap, or when? Who should I?
Maybe it's me. Yeah, that's basically my topic as well, because my origin is optical networks department in CESNET. And yes, we are trying to address that, but it's harder to work with optical equipment. It's hard to get it for experimentation. But we have something, we are doing something internally in CESNET, and also we are planning to work with optical equipment in GEANT. But what is available in GEANT is basically the OTN backbone, so we can have, let's say, lambdas, but it's not actual lambdas, yeah. It's a circuits over OTN. But what I am working on as my PhD thesis back in Czech Republic is virtualize similar way how to virtualize DWDM channels. So yeah, working on it. It's a work in progress, but early stage currently. We focused first on the packet-based resources in the GTS project. But there are some, let's say, side activities related. It's close to GTS, but mostly it's its own life now. But we know about each other, and I'm doing that research in Prague, for example.
Okay. So I would like to thank again the speakers and proceed to the next presentation. The next presentation is given by Monka Garbui. I hope, I'm pretty sure I misspelled it. So it is from Scuola Superiore Sant'Anna, and they will present us their activity on orchestration of services and how they interact with ONOS.
Good morning to everyone. I am Monka Garbui. I am from Scuola Sant'Anna, Pisa, and I will present mainly our activities with service orchestration and mainly the activities that currently use ONOS controller. So for the motivations, I will smart only 2 words since you are all familiar with these concepts. So nowadays we are noticing an increase in bandwidth capacity and reach capabilities. And in such a context, there is the network function virtualization and the SDN paradigms that are going in the direction of developing network virtualization and service abstraction. So in the context of softwareized networks, we have virtual network functions that mainly can be deployed within two scenarios. The first one is the use of virtual elements, such as network elements, switches, mobile nodes, which can contribute in deploying virtual networks. The second scenario, which is the topic of this presentation, is the use of virtual network functions as middle box services in order to differentiate the processing of data that traverse the networks. So this is the reference architecture for our service orchestrator. So mainly we have two layers: the network service provision and control layer, which mainly interacts with the applications in order to establish paths that traverse different middle boxes. And the second layer is the infrastructure control and management layer, which mainly regards the resource discovery, the resource monitoring, and especially the resource provisioning. So the main activities in our lab in the SDN and NFV area regard the orchestration of for the coordinated deployment of IT and network data center services, network orchestration of high available service chain paths, and the optimization of minimum latency composition of virtual functions. All these concepts have been validated and evaluated mainly within simulation environments, but also considering distributed microclouds using SDN interconnections and mainly using OpenStack and POX, Floodlight, and ONOS controllers. So regarding ONOS, the main activity is the deployment of middle box functions or virtual network functions, which allow the provisioning of services providing the establishing of data processing capabilities. So in such context, we need a straightforward interaction to adapt the service chains to ever-changing user requirements, and especially to recover from some degradations that might happen in the network, especially the congestion of the switches. So in this context, we propose a service orchestrator which allows for the effective interaction with the applications for the purpose to establish adaptive chains of network services. The orchestrator mainly is an SDN controller which is enhanced with network service orchestration capabilities. Mainly, we expose REST APIs that are used to set up and tear down a service chain paths. We also map the operation to embed these paths within the network. And the most important feature is the adaptation of the currently established paths to recover from congestion events for more reliability and also for a balancing beneficial effect. So these are the main building blocks of the orchestrator. It interacts with the applications through a REST API. So once a request is received, we take into consideration the current status of the network, and we send a path request to the controller, which can be an SDN controller such Floodlight or ONOS. And through the southbound interface, which is mainly based on OpenFlow, we set up the paths. Then we continuously monitor collect the statistics from the network. And in case of congestion of one or more switches or some degradation events, the already established paths are deleted and redirected through other switches that are not overloaded. For the evaluation performance, we have considered a mininet environment with the ABIL and core topology as an example. This orchestrator is mainly considered within two current activities in the 5GX project. So this is the first scenario where the orchestrator is deployed as a domain orchestrator within a multi-domain and multi-provider context. And the main feature is its adaptivity and the reliable enforcement of the paths, considering the current status of the SDN domain. The second activity is still within the 5GX project, and it is entitled My Cloud Anywhere, where the user can change from one domain to the other, connecting his computing and storage resources within a different administrative domain without taking care of the connectivity, which is handled by the multi-domain orchestrator. So regarding ONOS, this is the main architecture. So we have our orchestrator on the top of ONOS, which interacts with the applications through REST APIs and intent-based semantic APIs. The orchestrator communicates with ONOS through the REST APIs, and then the paths are established within the NSDN mininet topology. The interaction between ONOS and the mininet is handled through OpenFlow. For the REST APIs, we have mainly considered the intent framework. So for the path establishments, we have the high-level intents that focus on what should be done rather than how it should be done. Mainly, we have used the host-to-host intent and the point-to-point intent. For the adaptive capabilities, we mainly take into consideration the statistics that are performed periodically, and according to the status of the network and mainly the switches, we redirect the paths across switches that are not overloaded. So these are the main APIs that we have considered. The ones regarding the flows, the intents, mainly the host-to-host and point-to-point ones, and paths and the statistics. So to summarize, I will show two workflows of the main features of the orchestrator. This one considers the establishment of a composite path. So mainly when the request arrives, we evaluate the number of middle boxes that need to be traversed within the network. We take the first middle box instances. We try to identify which are the switches that are involved. And then if the path is simple and does not imply traversing the middle box, we use the host-to-host instance. Otherwise, we divide the path into different segments, and each segment is then established using the point-to-point intent. For the case of the adaptive features, we periodically take the statistics on the current status of the network, and in case of a congestion, we delete the path, all the paths that are traversing the congested switch, and we establish new ones by deleting the current ones and try to check if there are other switches available that can handle these flow entities. Thank you.
Okay, I'd like to thank the speaker. Is there any question from the audience? We have a question there.
Hi. Yesterday, I kept doing questions without introducing myself. My name is Mauro Tilocco with Telecom Italia. In one of your slides, you mentioned that you simulated a multi-provider environment. How was that done? By splitting the instances of the orchestrators, and so the ability to access to the network resources, or by means of separate northbound interfaces accessible to these separate providers? And was there any strategy then to access to the resources, avoiding, for example, cannibalization of physical or capacity resources by a given simulated provider?
Okay, if you are talking about this,
that's
okay.
the one, yeah.
This is not a simulated scenario. This is experimental one, the emulated lesson. It's not experimental.
Okay, I'll delete simulated. Sorry about that. But
and here, okay, each domain is mainly a virtual machine. Well, inside we have, for example, in our case, we have Mininet, and up of this we have the domain orchestrator, also in different virtual machine. And then all of them interact with the multi-domain orchestrator, which is in a separate virtual machine. And then all of these virtual machines communicate together.
Okay, but if the player, the multiple providers, did access to the same orchestrator?
No, they
and the
access only
orchestrator
to-
did some sort of brokering of the resources?
The providers access only to the multi-domain orchestrator, and then the multi-domain orchestrator splits and coordinates the information with the domain orchestrator.
Okay, so the orchestrator does orchestrate also the interaction with
Yeah.
the players that do access to the resources. Okay, thank you.
Which are the weak points you found? Because I followed the presentation, but it was not clear to me if it works. So, I mean, I've seen many of these type of ways of orchestrating things.
Yeah.
What I think would be useful to understand, if according to the evaluation you did or the simulation you did, you found weak points that we have to be careful about, because this is the usual thing. A lot of things can go wrong. So what is your experience? Thanks for that.
Okay, the weak points are to experimentally test our orchestrator and its features in, let's say, more realistic scenario. This is the first thing, because up to now we are using only simulation or emulation, but it's not tested in a realistic thing. The second thing is that regarding to ONOS mainly, we are considering simple APIs, REST APIs. So the simplest ones that are host-to-host and point-to-point instance, because we are starting with ONOS. So the next steps would be to go deeply further in ONOS and try either to change some of the applications or remove the interaction through REST APIs and try to integrate the orchestrator with the controller. But these are next steps that we are still investigating.
Okay. You saw what you're going to do, but you didn't mention the weak points. So you didn't provide an answer. That's my point. And any issue, I mean, security is not considered, I think. So it's very weak. So what should we look at?
Scalability, mainly. Yeah.
Okay, thanks.
I'm mostly involved in this project. I think there's not only a technical point that is weak, it's also the relationship. This project is focused on the interconnection of different domains. And all what we have today is some ideas that are based on BGP. But the world is a bit changed, and applying the same model maybe is not a good way to proceed, or it should be at least understood. So the weak point, in my understanding, is not the technical point; it's the architecture that is to be designed.
And
Looking at that architecture that you just showed, the multi-domain, I'm wondering about the decision of using multiple layers, two layers of orchestration instead of, for instance, having a multi-domain orchestrator and then ONOS controllers for each domain. So if you can give some lights on the decision to use this architecture.
Okay. I'll try because it's part of the project, but it's still running. But the main utility is that for each domain, we have specific technological context and provider context that are different from one domain to the other. So the main idea is that we keep the technical details to be handled by the local orchestrators, which are, let's say, dummy orchestrators, but that are aware of the technological details. And then the intelligence is put at the multi-domain level, which handles these local domains and then interacts with the providers and the upper layers. So this is the main idea.
also saw in one of your pictures work of you depicted the middle box. And I wonder if you are going or you already have some project to compare this multi-domain orchestrator even with the XOX environment.
No.
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 Okay. So if there is no other question, I'd like to thank the speaker.
Thank you.
We will now proceed with the. I will use the mic. We will now proceed with a coffee break, and then come back with the next session. The coffee break is for 15 minutes. We are a little bit late. We are 10 minutes late, so maybe to be back in 10-15 minutes will be great. And then we will go with the second session, which has 5 presentations, and then we have the lunch. Maybe we have some other.
No. Quindi se non ci stanno 5 presentazioni,
12:15. Ok, non è 12:30.
no, perché devi dare tempo di spostarsi alle 12:30 alla mensa.
Adesso non lo sapevo.
Adesso se poi sono le 12:20 non cambia
Ok,
niente.
però.
No, possiamo farlo. Solo un secondo. Certo.
Allora, non sono molto.
He's around. Are you going to look for him?
Well, yeah. I was able to grab.
Un altro Mac. Cosa?
È già il tuo?
Sì, sto provando, sembra che
funziona.
funzioni alla grande.
Ok.
L'unica cosa
Se-
è abbassato la cosa.
Se ti dà fastidio lo puoi far passare. dall'altra
Ok,
parte.
sei qui dietro le quinte che gestisce le
Sì, sì, siamo solo.
Ok, io ti avevo dato anche il video, non usare a questo punto, lo faccio
Hai
partire.
dato il video e l'hai
Ho dato
mandato
la
per
presentazione
nella
di
cosa.
Crezze. Sì.
Ah,
La
ok.
presentazione c'è anche un video.
Lo
però
fai
non-
partire.
Esatto.
Ma ha
così lo
detto che
posso-
non c'hai l'audio nel video, perché sennò devi attaccare
Esattamente.
il ripiatto.
No, esatto.
Quindi fai tutto tu.
Sì, perfetto, così lo blocco, lo faccio. Ottimo.
No, va bene, d'accordo.
Grazie.
Se hai bisogno, guarda qui.
Ti chiamo?
Ok?
Ah, apro e ti chiamo.
Sì, quello non lo devi fare.
Ok.
Nel mondo no, dovrebbe essere l'ultimo.
Prova. Ok, sono un po' bassino. Sono basso adesso. Se io faccio l'esempio. Non va adesso perché.
Vuoi concordare una domanda?
Ma guarda, le domande.
Facciamo una domanda. Se poi concordiamo la domanda, cioè, tu mi dici
Ecco, quello è fighissimo. Da politico, questo da politici.
Allora la conferenza lo facevo io e Serena.
Ma va.
Serena fece la domanda, io fece la domanda a lei. Così.
Ma beh, penso se non vede la Politecnica di Torino capiva.
No, beh, lui c'è la di Torino, dicevi.
Quando fai la domanda mica ti presenti.
Non è
No, ci sta.
Oppure
se fai una domanda intelligente ti fai riconoscere. Ti fai
però se avete
le domande.
No,
a me devo fare le domande come vabbè, fa le domande tipo quello lì a film.
Come si dice?
No, ma è stato non fa niente. È stato un po' bello.
Quindi prima sembrava che Interfaccia fra noi
Oh, I'm ready to even say.
Sarebbe la cosa migliore che ti permettesse di fare. Yeah, it's over there. Slide.
So please take a seat. We will start quickly.
Yeah. Yeah, already 20 minutes. Yeah, that's why. So, hope you had a refreshing coffee break. So, we're going for the second session of the morning and continuing on ONOS activities in EU. We will have the lunch. We will have the lunch break later on. I guess we will break around 12:20. So there is a possibility that some presentation will spill over after lunch. So I would like to start with the first presentation by Jan Usman from Giant. It is about, it is really visionary, so it's about Giant requirements and vision on SDN. I would like to, thank you, please.
Thank you. Hi, my name is Jan Usman. I'm an IP network architect at Giant Network. So I'll just go over what Giant Network is, why we're looking at SDN in the backbone, our kind of approach, how we've kind of taken on some of the use cases, collaboration with vendors and software-defined networking controllers, and then vision for multi-layer SDN controller in summary. So Giant Network basically is kind of a two main network. One is GWDM network, which is based on Infinera equipment, and the other one is IP/MPLS, which is Juniper-based, Juniper MX-based network. We run several overlays on top of the Juniper network. So we have global RNE IP network, which is basically the IP routing table for all the RNE networks across the world. And then we have Large Hadron Collider open network environment, which is LHC1. That's, again, a network dedicated for SIN, for big science. And then we have Internet Access Service as well, where we establish pairings and provide upstream transit service to the end rent. There are also a number of other services that we run. Giant Plus, which is a point-to-point service, MDVPN, which is a carrier-of-carrier service, and bandwidth on demand, and other services. But a lot of the traffic is mainly on the three main overlays I mentioned earlier. This is how the network looks like. This is the diagram from the Infinera NMS. So you can see our fiber routes. You can see the different network elements as well. And 10 gig and 100 gig lambda services are provided directly on this infrastructure. Rest of the services, all of them actually, are provided on this network, which is Juniper MX router. And then obviously all these trunks run on our DWDM network. Where we don't have fiber, we lease capacity from the commercial providers. This is kind of just showing the kind of a IP diagram where you see different connections, where you see the backbone link sizes. So it's a big network across whole Europe. You can see POPs in 30 plus countries, with 100 gig going across majority of the countries in Western Europe, and some of the Eastern countries. So the need for change, why we started looking at SDN, we're seeing exponential bandwidth increase. And I say exponential, it is really huge, obviously, with the Large Hadron Collider restarting with even more power. The traffic is growing significantly. We've seen year-on-year growth of over 60% in some cases on some of the services that we offer. So huge increase in traffic. The traffic on our network is highly unpredictable. It's not as the kind of a predictable as you'd see in a commercial ISPs, where you see a very nice curve going up during the day and then going down in the evening. And then it's a science traffic, so there could be a researcher sitting in the somewhere in the middle of the night starting a new data transfer. So you see a 2 gig average traffic a whole day, and suddenly the traffic is 20 gig. So we have to really plan our network based on the big science flows and large traffic instead of just 95th percentile traffic. There is obviously, as just a simple IP network, there is no application awareness. So as there is no application-based path selection, everything's treated, best effort. Where we need to integrate with other infrastructure. Giant is one of the infrastructure of Europe. There are other European Commission-funded infrastructure, and there is a need to integrate with them. So we need to start looking at ways we do things. We need to improve network visibility and reduce operational cost. Of course, the cost is one of the important bit as well. Programmability, you already heard Giant testbed service, where users can go and create a testbed across the GTS service area. We would want something similar where the big size user and researchers can program the network and use the APIs to link their application, data transfer application. When they need to transfer the data, it doesn't only look at the data, it also looks at the network and sees if the capacity is available there to transfer the data or not. Support for virtual network. And then obviously we want to remove dependence on the vendor software. We currently have Juniper in our backbone. And if we need a new feature, we'll have to just wait for Juniper to come up with that feature, test it in the lab, make sure that it doesn't break anything else. But we would really like the ability to kind of outsource or crowdsource some application, so it kind of makes it quicker to deploy new services. So we currently, as I mentioned, have a fully functional core router, which requires significant CapEx and OpEx. So that's one of the major problem that we have. And obviously the view of the network is very router POP centric view, where you're looking at it, what's happening in that particular link or that particular POP when you need to increase capacity in a POP and a router or a link. And currently, obviously, because as I mentioned, we don't have any priority for different types of traffic or making sure that we prioritize research traffic or commercial traffic or something like that. We don't do that. So we solve the problem of these unpredictable flows with over-provisioning. Obviously, this ensures the network reliability and delivery of traffic despite failures, but that also means that we have to install a lot of capacity. We obviously use protocol metrics or to route to shortest path. There is no consideration of link utilization. So we're hoping that when we move along, start using more of the SDN and bring this intelligence into the network, so it knows about the link utilization, and if it needs more capacity, it can request to the lower layers and get more capacity. And I'll go into that in a bit more detail in a few slides. So what we basically need is obviously a high-performance network which can handle the growth that we're seeing in the traffic. We also want to reduce the network cost. We want separation of hardware and software, so we can buy the hardware based on the features that we need, and we can choose the software based on the services and protocols we need to support. So we could choose ONOS to do our bandwidth and demand, for example, or STN/IP, instead of just relying on the vendor software to provide this. So our approach when we started looking at it, what we did was we actually defined capabilities that we needed, or the use cases we called them. So we first needed SDN-based layer 2 circuit, we needed SDN/IP, we needed software-defined exchange points, network in campus, that's another use case that we defined, infrastructure and network as a service, and transport SDN. So once we had defined different services that we had, we looked at the functional and operational requirements. Then we started looking at the test use cases. How can we actually test them? What do we need? So we bought some hardware. We bought white boxes, Corsa hardware, Infinera OTN cards, and started looking at the SDN controller framework. We looked at Open Daylight, ONOS, vendor backend. And then we also looked at the open call projects that Giant had funded in the past, like DINPAC and Dreamer, and then did the gap analysis. And based on that, we actually selected ONOS as a controller of choice to work because it had quite a lot of the features that we were looking for already. We selected the hardware from Corsa because it has deep packet buffers and it can handle multi-table pipelines and a couple of millions of flows in the flow entry tables. And Infinera PXM because Infinera is our DWDM provider. So requirement for SDN, it wasn't just coming up with the use cases. We actually went to quite a lot of details into coming up with different requirements. So we had redundancy and high availability features for controller. We had scalability. How scalable does the solution need to be? So number of open flow switches that need to be supported, number of BGP pairs, number of IPv4, number of IPv6, all these different things. It wasn't just coming up with the kind of a use case, but also the functional requirement. So switch related, what do we need from switch? What do we need from controller? Support for switch pipeline, number of open flow rules supported in the switch, speed of flow installation, and all these things. Obviously, along with that, we also had monitoring and operations. So we had kind of how do we monitor if we had to bring these services in operation? How is operations team going to manage them? So this is kind of how we defined requirements for each of the use cases, and then in turn we also then defined how we're going to test those requirements in the lab. So a lot of work going on these. Then obviously a lot of the use cases, Kostas, my colleague, will go into more details on the different use cases that I've explained earlier. But I'll just mention the bit of a collaborations and the work that we are doing with the different vendors. So we are working with Corsa to evaluate their switches as a replacement for our routers and small pops and Giant, where we only need a couple of 10 gigs. We're working with OnLab to develop applications like BOD and SDN/IP. The bandwidth and demand application we've already created. We have demonstrated that, and we'll be piloting that in our backbone, hopefully by end of this year. And then we are also working with Infinera to develop the REST plugin for ONOS, and that implementation was also completed and tested in the lab last week or so ago. So we now can control the Infinera OTN with the REST plugin in ONOS to create and delete circuits on Infinera layer. So this is the Transport SDN app that I'm just mentioning. So we work closely with the Infinera to develop the solution for OTN. This is how it looks. We have an SDN controller, which is ONOS. ONOS there, which speaks trust to OTSV, which is Infinera provided open transport switch, which then enables us to manage and configure the OTN layer on Infinera. We use ONOS to do that now. And obviously, this brings a bit more intelligence to the core and reduces over provisioning because we're using OTN layer instead of 100 gig everywhere. We can now just kind of slice up the circuits to the capacity that we need. And also it paves the way for the multi-layer interaction, whereas currently we now speak directly to DWDM layer, and we also speak directly to the layer 2 equipment Corsa. So hopefully these two then will be able to enable some interaction between the two layers and enable some multi-layer SDN. With collaboration with Corsa, so we are delivering layer 2 and layer 3 SDN data plane functionality by leveraging the Corsa hardware. As I mentioned, it supports 10, 40, 100 gig and has deep packet buffers in it. So it can handle large elephant flows, and it has quite a lot of capacity to handle full internet routing table as flow entries in the Corsa switches. We, as mentioned yesterday, Ali mentioned it, that there is, with OpenFlow 1.3, the additional complexity is that you have a multi-table pipeline. So based on the application and use cases we have, we've kind of worked with Corsa to develop a tailored multi-table pipeline for us, which handles all our use cases and enables us to use ONOS with the Corsa switches. So collaboration with OnLab, we've worked with OnLab for quite a while now, over almost 2 years now. We've submitted a lot of codes to ONOS for different applications, BOD. One of the major one, I think, is the migration from the intent framework to flow objective framework, which enabled the use of OpenFlow 1.3 multi-table pipeline with SDN IP switches, with Corsa switches. And this was a kind of a three-way collaboration between Corsa, Giant, and OnLab to implement that. And it was implemented, tested in the lab a couple of months ago. We are currently testing it in our own lab in Cambridge. Now, we also, as I mentioned, have done a three-way collaboration with Infinera on the transport SDN use case. Again, Infinera, Giant, and OnLab were involved in creating this application for our use, and I'm sure Kostas will cover a little bit more on the development part of this. So this kind of just shows you a little bit of the way that we have gone from current architect and the vision. So the current network architecture is quite simple. We have giant routers, which have 200 gig going into DWDM equipment, and then they go into either one neighbor or the other neighbor, and that's how the network is set up. And so the revised network architecture with Infinera PXM card, the packet card or OTN card, is that we have 100 gig going into the packet card and Infinera layer, and we provision the circuits based on the capacity, based on the traffic demands, rather than just having 100 gig everywhere where we don't even need. So you see, there's, instead of having 200 gigs, we have single 100 gig. You could have 50 gig going to one end and 50 gig going to the other end, or you could have based on whatever demands that you have. So this is basically if you manage those cards with Infinera NMS. But what we've done is we've created this transport SDN app with which you can see SDN controller on the top right over there. It talks to the OTSV, which is Open Transport Switch from Infinera, which then sends messages down to the PXM card. So the trunks now are controlled by the OTS, and OTS is then managed and controlled by the SDN controller, which in this case is ONOS. So ONOS controller in this diagram actually is talking to our layer 2 switches, and it's also talking to our PXM cards, and it can provision circuits on both layers. But because this is independent right now, so if you wanted to create a circuit on the optical layer or OTN layer, you'll just send the signal down to that, or if you wanted to create a layer 2, you'll send signal down to layer 2 SDN switches. There is no interaction between the two layers. Both of the layers can be managed by the same controller. But what we really want is something like this, where you have this switch multi-layer SDN controller. So SDN controller is talking to both layers, but then those layers are able to talk to each other. If on layer 2 we run out of capacity or we need more capacity, it can automatically signal down to the OTN layers and request more capacity. And that's kind of a vision. And that's why we were really keen on making sure that we get one controller and we install and deploy the apps for both managing transport layer and managing the layer 2 on the same boxes. So right now, as I mentioned, we are working with Corsa for layer 2 and layer 3 devices. We are hoping in future, again, as this is a long way away, as you'll see from the previous diagram, there was routers and layer 2 switches, but here we've replaced even the routers with this SDN switch, because in the future we are hoping that we'll have the capability to run even IP, full internet routing scale IP service on those switches and have this multi-layer SDN controller, which enables us to dynamically manage the capacity, backbone capacity. So this is kind of a main long-term vision for us, replacing the full layer 3 devices with the WAN optimized switches if possible, where possible. Obviously, in some of the POPs, in Western Ring especially, we even run out of chassis for MX960. It's not easy to replace those routers. But in smaller POPs where we only have multiple 10 gigs, we think it might be possible to do that, where we don't need full internet routing table. We only have 30 or 40 gigs of capacity requirements. And again, we cannot use the OTN PXM cards everywhere, but where we can, this is the architect that we are targeting for. So in summary, the kind of SDN backbone solutions are under preparation to deploy in pilots. We have tested most of the use cases that have gone through in our labs, and now we are kind of working on deploying them in our backbone to pilot them. There's a SDN BOD application which has been tested and will be piloted. There's Transport SDN which has been tested, will be piloted, and we are also now currently testing SDN IP. We continue work on ONOS and SDN apps. We'll continue to develop more whatever functionality we need and we think it's missing. And we are upgrading our lab for pre-pilot testing. We bought new Corsa hardware with 2100 series, which is a little cheaper and also offers the same functionality to us. So that's the hardware we'll be using. That's the hardware that the GTS, Giant Testbed service, will also use. So you'll be able to actually go to a GTS web interface and request resources, and you'll get resources from DB2100 series to run your own experiments. And obviously, as it goes, we will constantly evaluate the choices and architects, and as we get more information, we may revise the architecture, the vision, and the controller choices. So that's just a kind of a work ongoing onto that. And that's it for me, I think, on time.
Thank you.
Any questions?
Any question for our speaker? We have one.
Correct me if I'm wrong. You mentioned that you're using REST API to configure the Corsa Infinera switches, right?
Infinera, yeah. Corsa talks OpenFlow 1.3. Yeah.
So if you change the hardware, you need some new southbound abstraction.
That's right. So if we did replace our Infinera with Sienna, let's say, then that would be required. Change would be required. But because we've bought Infinera about 3 or 4 years ago, we don't think we'll be changing it anytime soon. That was one of the things that we did think about, saying maybe if it did speak OpenFlow, we wouldn't need to, and we'll be really vendor agnostic. But unfortunately, that's not the case in this.
Have you ever thought about using some new standard like OpenROADM or something?
I don't know. No, I don't think so, because I'll have to check with my colleague, but I highly doubt it. Yeah.
Thank you.
Any other question? If not, thank you.
Thank you
for your presentation. So we looked at the requirements and vision on SDN from Giant. Now from Kostas Stamos from GearNet, we will hear about the use case in Giant related with ONOS activities. And
Thank you, Domenico. So, yes, my name is Kostas Stamos, and I'm working with Mian on the Giant's SDN activity. So I will continue basically from where Mian left off. So as he described, we came up based on the requirements for the Giant network with a set of use cases. So one of them is the SDN bandwidth on demand, with the purpose of having the bandwidth on demand service operate over SDN. Then we have the SDX, both for layer 3 and layer 2 circuits. The optical transport SDN use case with the Infineras. And we also dealt with the use case that we call the network in the campus, with the basic aim of extending services like the bandwidth on demand over the last mile and investigating other protocols like netconf aside with OpenFlow. So starting with SDN bandwidth on demand, this use case is based on the DINPAC application, which was initially developed in an open call project funded by Giant. And this was developed as an application over Open Daylight. In the context of the project, the team migrated this application as an ONOS and made it an ONOS application. And the purpose is to be able to offer multi-domain bandwidth on demand services over networks that may be SDN or may not be SDN, and offer the bandwidth on demand service by enforcing quality of service constraints such as rate limiting. Also, a major part of the DINPAC application is to have clever algorithms that make efficient use of the network capacity, able to relocate flows or disaggregate and send them on different paths for better efficiency. And furthermore, it can handle failures with quick recovery to backup paths. And for this purpose, it actually uses a pre-computation of the backup paths. In general, you can see in this diagram an example of how the BOD service operates. So basically, DINPAC is installed as an application within ONOS, and it uses a custom API to talk to an NSA module, an NSA agent, which is the module that understands the NSI protocol. And the NSI protocol is used for negotiating the connection with neighboring domains. So as NSI is a standard, it has been implemented in various instances by various organizations. So it gives us the possibility to interact with other domains offering a similar service. And in the case of our use case, we have DINPAC that is able to instruct ONOS to build the flows in an SDN network. So in this picture, you can see with the large blue arrows the main areas where we intervened. We migrated DINPAC from ODL to ONOS, and we implemented the interface between DINPAC and the component responsible for understanding the NSI protocol and handling the interdomain exchanges. We also made some extensions to the ONOS UI, so it's possible to use the ONOS UI to request a service, but just for a single domain, For a multi-domain case, there is a special UI that is already used in the on-demand service and which can also be used to extend the services over SDN domains. Moving on to the SDX. For SDX layer 3, our requirements were to be able to operate the SDN network as an internet exchange point infrastructure. So we want to offer IP transit service to the customer using BGP for communicating with the peers. We would like the administrator of the SDX to be able to dynamically configure the peers. We would also like to be able to have configure peers residing on the same network subnet. And we would also like to have direct communication between the peers by not introducing an additional layer 3 hop. So for this use case, SDN IP is already there in ONOS and was basically fit for the task. What we did was just do a few modifications or additions to SDN IP so that it covers the exact requirements that we had for to operate as an SDX. And basically the approach we took initially was to create a duplicate application that is a copy of SDN IP, but with some modifications in the relevant functionalities. In the short-term future, we hope that this might not be the case, so we don't have any more duplications, and that we're able to have a single application that can, as SDN IP operates, but can also be configured to cover our SDX requirements. So I'll just highlight quickly the differences between SDN IP and the SDX. SDN IP, the way it's designed, it requires that the external interfaces towards the peers are configured with IP addresses belonging to the peer network, the peer subnet. So this does not make it possible to have them belong to the same subnet. So if we wanted to have, for example, connectivity with peers on the 10.0.0/24 subnet, we couldn't do it with the SDN IP, so we had to make a small modification here. Also, SDN IP operates as an IP transit network, so it has one additional routing hop at the internal BGP speaker. A root server kind of functionality. We would like to eliminate the intermediate hop so that the BGP peers appear as to be directly connected at the layer 3. And finally, we also wanted to add the capability to SDN IP to support multiple BGP speakers for a single peer, which is also an extension we did to SDN IP. So this application we created, which is, as I said, is basically SDN IP, but with a small set of additions, is called the SDX Layer 3 application, which we made available in the ONOS samples repository. And it's a superset of the functionality of SDN IP. It has the capability to configure the BGP configuration during runtime. It can also use a separate and independent application that we have developed for exporting flow statistics through the IPFix protocol. For SDX Layer 2, we developed another application, again, made available through the ONOS repository. In that case, the purpose is to provision Layer 2 tunnels between edge endpoints in the network. So we created this application that creates it uses the intent framework of ONOS in order to create the circuits, and have ONOS translate the intent of connecting the two endpoints into the appropriate flow rules and install them in the SDN switches. So again, this is the diagram of where we intervened, both CLI and UI for this application. It is able to build the circuit using 3 types of tunnel modes based on MAC addresses or VLAN or MPLS encapsulation. And it supports incoming untagged traffic, or VLAN tagged traffic, or tagged traffic that needs to be modified in terms of the so this is a typical, let's say, ONOS application. You can see here in the dot the internals of the application. It communicates with the GUI and the CLI for accepting commands by the user, by the SDX administrator. The underlying ONOS services in order to provide the user requested service. And it can also run in several ONOS deployments, and we hope it can also scale to a large extent. We want this is something that we need to and want to investigate and verify in the short term. And another last interesting thing about the SDX Layer 2 application, it provides an abstraction of virtual SDXs. So it gives the some sort of let's say separation in the at the administrator level, so we can have completely different SDXs, each one having its own edge connectors and connecting different endpoints operating over the same physical network. The other use case, as I said, is the network in the campus, and the idea about this use case is to be able to extend services such as bandwidth on demand to networks that use, for example, legacy equipment, or for various reasons might not support OpenFlow. We worked with the ONOS community and Andrea Campanella quite extensively in order to extend the support for netconf in the ONOS netconf driver, and also implemented a small extension in the UI of ONOS and in the a part of dealing with the authorization and user profiling in order for a user to be able to select and map the physical elements that he would like to map to the underlying service. About the transport SDN use case, you've heard already from Ian. So there, our basic effort is around extending the southbound interface in order to be able to talk to the InfiniRoute ESV plugin, and as Ian said, this has already been achieved. What we would like to do, however, is to solve the problem of having the OTSV controller, which is a controller that controls multiple devices. It actually controls the whole optical network. To be able to have it seamlessly interoperate with the way that ONOS understands the topology, the way that the intent framework breaks down the required flow rules per device. So we are in discussions with the ONOS community on how to best achieve this. And this is also a concern by other similar projects that I assume you will have the chance to hear. And a more mid-term goal, let's say, is to also make this an integrated application, an integrated use case with ones we presented before, so we can take advantage of efficiencies in the way that the network capacity is provisioned. So this is basically what we have done until now. And initially, we selected ONOS after going through our requirements. And in general, I can say that our experience has been very. In this room, there are several developers from Giant that can possibly provide more details on how they have collaborated with the ONOS community. But my overall understanding is that we have met with a very helpful community and an open community that was willing to engage with our requirements and listen to any problems that we had and try to resolve them together. And also, I think the developers can attest that in general, the development experience with ONOS has been positive and relatively lightweight. So it does not require, I mean, getting started with ONOS doesn't require a lot of a very steep curve that might discourage some. What are the next steps? We want basically to transition from the proof of concepts that we have until now to pilots and then pre-production. So we would like to basically the applications to make sure and verify if they live up to the kind of scaling that would be required for such a transition. Try out the new Corsa platform that the GTS guys discussed about a while before. Until now, we have been using for the layer 2 and layer 3 use cases. We have been basically testing on the 6400 Corsa platform, but we would like to see with the new platform that Giant has procured. And we would also like to move towards a better integration of the use cases to take advantage of multi-layer efficiencies. So that's basically my presentation. So if you have any questions.
Thank you. So, any question from the speaker? Okay, if not,
okay.
Thank you very much.
Thank you.
So the next speaker will be actually me, so quite easy to present. We should switch to the laptop if possible. It was done in, yeah, great, done. Okay. So now we're going to present together with my colleague Michele Santuari from Creanet, a new project, which is a project tackling application-centric IP optical orchestration. Is doing this job of the combination of multi-layer control with the ONOS control. So before talking about that, let me start with a brief introduction. I don't want to bother you with the fact that actually applications are the driver for the evolution of the future networks, and they are increasing in size and bandwidth. And the most important thing is that they have a very diverse requirements. If you look at, we know that by 2021, the video will account for around 70% of the mobile data traffic. But most of it, what is really important is that not all the video has the same requirements. If you look at the live video for TV broadcasting, it has some requirements in terms of latency availability, while video that is used for CDN or has totally different requirements. And most of it, applications do not care about what we do in the network. So they don't care about how the network is composed, what are the nodes and all these things. They only care about the service their traffic receives. So by looking at the current transport networks composed of mostly IP optical equipment, as it has been discussed many times also during the previous presentations, we have seen that from the point of view of the application requirements, there is quite an inaccurate mapping between what are the needs of the applications and the service they receive in the transport network. Because you have the application layer, you have a fixed transport layer, which is usually the WDM or flexi-grid optical networks. And in the middle, you have a grooming layer, which is basically AP, which grooms the traffic from different applications and aggregate the requirements. So they are all served by the same, they get the same service. What we want to do in this Acino project, we want to enforce this application-centric concept, which differentiates the service offered to each application at each layer of the transport network, so that the network is adapted to the needs of the applications. So if you look from the bandwidth perspective, of course, there are some services that have bandwidth enough to be directly served on the optical layer with different requirements, while for other services, you can group them and go for application class requirements. So the idea is basically that if you have, for instance, a TV broadcasting application and a live TV application, they have different requirements in terms of latency and bandwidth. So you have two layers. One is the optical layer, one is the AP layer. And if you look at one of the possible operations you can do, which is resilience, for instance, restoration, you can operate restoration at the AP or at the optical layer. According to such requirements from the application, with a centralized with a centralized orchestrator, you can apply either restoration at the AP or at the optical layer according to what are those requirements. And that's basically the idea. That's the application-centric concept we want to enforce in the Acino project. So we basically have three pillars there. Is intent-based networking. Applications, as I say, do not care about how the network is composed and what are the network operations at the end. They only want to have, for instance, a meshed connection between sites, and they want to say, okay, I want this latency, and I don't want my traffic to go down for more than 5 milliseconds, for instance. Those are the requirements that they have to tell us. And we are building on ONOS novel intents and primitives and interaction and negotiation procedures. This is more researchy, I understand. It's less operational, but we believe it can be a nice, they can be nice features for the future, as well as for the application-centric optimization. Of course, once you understand what you want from the network, you want to do a multi-layer provisioning of the resources, as was, let me say, foreseen by Mian in the 2 presentations ago. Something that can merge the 2 layers and then can have them interwork in order to provide the right capacity and the right requirements. So, working on what is in operation planning, meaning re-optimization, and a feature that we are thinking that is that we can expose that is related to what-if scenarios, where an operator can ask to the controller what happens if I remove this link, and he sees actually how the network re-optimizes. And finally, another pillar is, of course, network orchestration. Once we have done, once we got what are the needs of the applications, once we got, we know what to do with the network, we need to enforce it. So we are doing multi-layer modeling of the network, and at the same time, of course, we are trying to understand what we have to control, which is not only devices, as Giant is doing with in Finera. We are also controlling, controllers, because usually vendors sells equipment, especially in the optical domain, sells equipment with a control plane. So, which is very difficult to detach from the software they provide you. So it is much better if you can control a controller. And in this sense, this is the implementation that we are foreseeing. So we have a network orchestrator that exposes northbound APIs, intent-based northbound APIs towards applications, and it is based on ONOS. So we are developing on top of the ONOS framework, and it has southbound APIs towards, which can be layer 3, layer 1. Actually, we don't have, we have very few things on layer 2, but mostly layer 3 and layer 1, because the project is about IP optical, and or can control directly some equipment. For routers, as I said, is much easier. While when it comes to optical, at the moment, I would say the most practical thing is to control a controller. So this provides a multi-layer optimization, which abstracts from layer 0 to layer 3. And it is a hierarchy of controllers, which if you develop enough southbound interfaces, it is, that was a question before, if you have many vendors, you need to develop as many interfaces as long as they do not adopt a common interface for it, which can be the transport API defined by ONOS or some by ONF or something different. And it is, of course, suitable for multi-domain at the moment. So before leaving to a short demonstration, I would like to introduce quickly two of the use cases of the project. One that is quite fancy is what we call secure transmission as a service. Basically, we know that security is very important for service providers, and traditional services are actually performing encryption at the endpoint. So you have HTTP encryption. But if you have trusted endpoints, you can basically enforce encryption in the middle of the network. So, and in some vulnerable parts, for instance, if you have a data center interconnection over a public network, you can do this at different layers. As I was saying before, you can do at AP, so you can do IPsec, you can do at layer 2, MACsec, or you can do a layer 2, layer 1. So if you look at a simple example with 3 optical nodes and 3 routers on top of them, and we assume that we already have 2 light paths between router 1, router 2, and another one between router 2 and router 3, which basically are creating 2 IP adjacencies. And we have a service request for a secure app that requests low bandwidth. So we can go for IPsec. We configure an edge-to-edge IPsec tunnel between router 1 and router 3, and we let the traffic flow and the same route of the other traffic. So this is quite easy to deploy. It is flexible and independent from the underlying optical infrastructure. We're using existing optical light nets. But you're increasing the processing delay because you're gonna encrypt packet by packet. And what we have experienced, and it's not only us, there are papers on that, you of course have some reduced throughput. On the other side, if you have a service request that is asking a secure app with high bandwidth and low delay and processing and those things, you can actually establish an optical line path over some optical line cards with encryption capabilities. One of our partners in this project, which is ADVA, has line cards at the optical layer that can encrypt the traffic. So the application traffic is now routed over the newly established link. Has pros and cons. You have high throughput, so you don't have any processing delay, so your application can be satisfied on that side. However, it requires a custom infrastructure. You have to deploy those cards, and if you have them deployed, you don't want to use it then for all the traffic you have. It's a scarce resource then. Depending on what are the network conditions, you may want to do encryption and security, either at the IP or the optical layer. It depends on what are the application's requirements, and you want to enforce it by using the orchestrator we are proposing. We have other use cases which have been published in a UCNC paper this year, but I would like to go quickly through to the presentation of the demonstration in which we do policy-based restoration in IP optical transport networks. And it is so about restoration. We know that for resiliency, there are different procedures that one may apply. You can be proactive, so set up some protection strategies. So when the failure occurs, automatically the network switches to another path or goes around the failure. Other solutions are reactive solutions, which is usually called restoration. And you can do it at the IP, at the optical layer again. And if you do it at the optical layer, you basically establish a new circuit, a new optical light path that goes around the failure. While if you use IP restoration, you basically reuse existing light paths to diverge your traffic at the IP layer. You are using IP adjacencies that you have already established in the past. So of course, these are these are network operations that have different characteristics. If you look at the responsiveness, the cost, or the offered capacity. Of course, if you look at the responsiveness, the optical restoration is quite slow. In order to establish a new optical channel, it usually requires seconds, maybe even more in some cases, but let's stay in the order of seconds. While if you want to do IP restoration, just have to switch the routing tables, it can be very fast, and it is usually commonly referred to be as below 50 milliseconds. But the cost, of course, and also the cost, it's very high for optical because you need additional resources, while it is low for IP. On the other side, you have offered capacity that is guaranteed at the optical layer, while it is not guaranteed at the IP layer. So again, as in the previous case, depending on what are the requirements of your application, you want to apply a strategy either at the IP or at the optical layer, or combine them in some way. So the rationale demonstration is that we do not imply any logic for designing what is the kind of restoration you want, but we allow the operator to tell us, okay, look, I want to have an IP or an optical restoration, and I can communicate this to you via intents, and then ONOS configures either the IP layer or the optical layer consequently. So I will let my colleague Michele to present you the architecture, the steps, and show you the demo afterwards.
Thank you, Domenico, for the introduction of the use case. Our architecture, on the top you can see our orchestrator that has been developed on top of ONOS. And on the bottom side, we see the testbed. This is a real testbed deployed in Telefonica premises, and where we have 3 Juniper router, some ADVA ROMs. The ADVA ROMs are controlled by an optical hypervisor that is called Optical Virtualization Controller, OVC, that is able to expose the topology and also the capabilities of the device via an OR-bound REST to our orchestrator. The orchestrator communicates with the OVC using REST, an extension of the REST, and leveraging on a driver that is called the COP, that is a protocol developed during a European project. Instead, for the EP router, we are communicating using netconf and configuring via netconf using a dedicated driver that is called the Juniper driver. And in the core, we extend the intent framework to provide the so-called application-centric intents that are enriched with some capabilities to provide the decision on what we want to achieve as a restoration technique, basically EP or optical restoration. And finally, these interfaces are exposed to the northbound interface and the user. We are going to contribute back to the community, the ONOS community, with the 2 drivers, and maybe also with some feature for the intents. So this is our scenario. Here, our testbed. The first picture shows the optical restoration. We set up a light path between the 2 ROMs, and we configure some EP routes on the Juniper automatically using our orchestrator. And when a failure occurs between the Juniper one and the ADVA ROMs, on the orchestrator will be able we'll be able to reroute the traffic, creating a new light path between the two ROMs. Instead, for the IP restoration, the starting point required 2 additional intents between J1 and J2, and between J2 to J3. In this case, we will have 3 optical light paths installed in the network. Or basically, we don't install new optical light path, but basically we add some EP routes on the Juniper to reroute the traffic on the existing light path already installed in the network. To the demo. So here I am showing the devices covered by the orchestrator. Basically, we have 3 netconf devices and 3 ADVA as the testbed I already showed. Also, we are able to discover the links. Here you can see the graphical interface of the orchestrator. We have 3 ADVA routers and 3 Juniper routers interconnected directly to the ADVA routers. And finally, we have 3 hosts that are simulated via the loopback interface to be able to connect them and to be able to ping the different hosts in the topology. We don't have any intent installed in the network, and this is the GUI of the ADVA optical virtualization controller, and I'm showing you that we don't have any intent, any service installed at the optical layer. And here I want to show you that we have some basic routes on the router that are used to manage the connection between the orchestrator and the devices using netconf, and also to access the CLI. Then what we will do, basically, we will request a new application-centric intent with a constraint that is called optical restoration. So basically, we are asking to our orchestrator, if there is a failure, please reroute, creating a new dedicated light path on the network. So basically, our orchestrator will install a new optical light path and also some EP routes at the Juniper, in the Juniper router. Here we will see the intent that has been installed. And finally, these are the routes. One route has been added in addition to the previous one. And also here, this is Juniper 3. This needs to go back to the other host in the 2 endpoints router. And finally, here we have the optical light path that has been installed. And as you can see here, it's called H01. This is important because we will see that when there is a failure, a new light path will be created. And so we are pinging the 2 loopback interface on the router. And as you can see, we have connectivity between them. And then we will simulate a failure by setting a port down on the Juniper router J1 that we will see on the topology now. Okay, so basically we have disabled the ports. And so ONOS will receive a notification that the port goes down. And it will reinstall the intent, recompile the intent. As you can see here, we are in installing state. And here in the topology, we don't have anymore the links. And a new optical light path has been created to accommodate all the requests finally installed in the network. And here, the optical light path has changed to H03. So basically, we have created a new we have a lot of delay before installing the light path, as you can see, because it requires some time to be accommodated on the network. But finally, we are able to restore the path. Then I will move to the second scenario, just to remember that is this one. So EP restoration, we will install 3 intents between the Juniper routers, and then we will have a failure on the control plane. So basically here I am installing an intent between the 2 hosts using the IP restoration in this case. So we don't want to reuse we want to reuse the optical light path already installed in the network. Then that has been installed, but I would like to show you the final result. That is, we have so we have installed all the intents. Basically, we have 3 intents installed in the network with 3 light paths installed that guarantee the connectivity between the hosts. So basically, as you can see here, we have 1 intent installed and the other. So here we have connectivity between all the hosts, and finally here we have all the 3 light paths installed in the network, Achino 3, 1, and 5. Then we go for pinging between the two hosts that will be involved in the failure. So now again, we will set up, we are going to disable the port between the J1 router and the ADVA RODMs. Our orchestrator will react immediately, and it will take less time to reroute the traffic. We are speaking about seconds. We can improve this, of course. And after some seconds, we are able again to establish the connectivity by rerouting at AP level. As you can see here, the next stop is the same for both entries because we are reusing the existing light path already installed. And here you can see that we have only two light paths between the RODMs, and we don't have any more light path interconnecting the other two RODMs. And finally, the OVC graphical interface will show that we have only one light path, but the intent, of course. So here, okay. So we have only two light paths installed in the network.
Okay.
Okay.
Thank you, Michele, for the presentation. So if there is any question on... Oh, sorry. There is a question from the audience, not from me. Okay.
Thank you. José Loret from the Technical University of Denmark. As I understand, you have used the interface of ADVA for all the controlling.
For controlling the optical controller. Sorry, I don't see.
You don't use OpenFlow with optical extensions?
No, we don't use OpenFlow with optical extensions. First of all, there are a lot of design choices behind that. When it comes to optical, I'm not sure that OpenFlow is the right kind of protocol you should use. It has been designed for a different purpose, and adaptation to optical is just really an adaptation. It serves a different purpose, in my opinion. But however, you can use it, of course. In this work, we directly talk with the controller, then interfaces with the devices. It can be then that it interfaces with the device through GMPLS or whatever, or NetConf or whatever other protocol they're using. But we actually don't care because the configuration of each device is carried out by the technology-specific controller. This is usually why. This is usually because if every kind of, especially in the optical, every vendor has its own protocol to configure their own devices, its own also some procedures to regulate, for instance, amplifier power and all those things. So what is happening is better that you directly talk with the controller and they take care of configuration and small precision parameters that they usually do at the optical layer. While in the IP, you can use something different. In this case, a driver we developed for to use a NetConf with Juniper, right? Yes, exactly.
If you use the proactive configuration of all the switches, optical switches, then it's right. But in case you have to have a reactive reaction for the restoration at a delay that is essential for the optical switch.
Well, optical restoration is always the point is that when you do optical restoration, you basically establish a new optical channel, and usually it really and according to my experience in operational networks, it takes seconds or even more. So if you add a 1 second over multiple seconds of delay, or I guess it's even less, it doesn't impact that much. At the AP layer, we need to understand how to reduce it. We are still slow, so this is something we are experiencing. But at the optical layer, it is not a problem to me. This is my feeling.
Hello, this is Arthur from PSMC. You said that you have a driver for Juniper, and that for the ADVA you just they use the controller.
But we have a driver. We
This is
developed a
also
driver
the-
also.
yeah, okay.
We have another driver.
Okay.
It is Michele can comment a little bit on that.
Yes. The driver is the COP driver. This is, as you can see here, basically we have oh, I cannot show you the slide, but not a problem. Here you have the COP driver that is a protocol that has been developed during.
Yeah, I just was confused because the last day we learned that the drivers are and after the driver there are the abstraction layer, and then we see the driver for Juniper and some magic controller from the ADVA, and it's called controller, not the driver. And I just want to ask about this. This is driver for this controller in ONOS or something else? Thanks.
You're welcome. Thank you for the question. Any other question? Okay, yeah. Maybe we let's start with one of them, and maybe we can. We'll see if there's time enough for.
I haven't understood if you are able to manage multiple intents to the same pair of hosts. Think about an host with different applications, with different requirements.
Yes, this is totally possible. We don't see any real problem with that. If you talk about then how to select traffic at the source, it is another kind of problem which is quite relevant. But with respect to managing the different intents, the very big problems. That was quite quick, so maybe thanks.
I'm wondering which level of programmability provides the ADVA controller.
This is quite interesting. So they are developing the possibility to, for the moment, we give them some endpoints and they select they expose the full network. However, for the establishment of a light path at this very moment, we give them the endpoints and they select what is the path, which is usually on the shortest path, which is reasonable choice. However, they are developing features in order to let us select what is the path over the network, which will potentially allow us to select some paths for some applications that have more priority than the others, without going always on the shortest. It's a work in progress.
Why the choice of COP for the interface?
That's quite easy. They had developed that before, and they are using it. Well, it is also okay. There is also another reason which is quite important. The COP is a subset of the transport API, which is a definition in the ONF. So it's quite a standard for having an interface for transport network. So it makes sense also from the standardization point of view to have something that is not just a project-specific interface. Okay, thank you very much for the questions. I get back to the chair hat, and I need to switch one presentation because we will not be able to finish all the presentation in the morning. So we now have Francesco Lucrezia, which did a joint work between CRIENET and Politecnico di Torino on an intercluster ONOS network application. The acronym of this is ICONA. So Francesco, please.
Very much. This makes me feel short. Okay. No, later.
Okay.
Okay. Good morning. I'm Francesco Lucrezia from Politecnico di Torino, from the Net Group Research Lab. And as Domenico said, I'm working with CreateNet, in particular with Matteo Gerola, is the lead of the project, and Michele Santuari, person who guided me through the development of the tool. ICONA is the acronym of Intercluster ONOS Network Application. As the name suggests, is a tool aimed at provisioning a peering control system between cluster of ONOS. Just to clarify, a cluster in the ONOS terminology is a set of controllers, distributed state for high availability, resiliency, and robustness. but I will use the term cluster to refer also both the set of controllers and the underlying network controlled by such cluster. Okay, I will briefly explaining the motivation, the capabilities of our tool, an overview of the architecture, and a short demonstration, a video demo for the state of the project. Very simple demo, not articulated as the previous one. What is Icona? It's an open source ONOS application. Is some part of the APIs are already public in the ONOS samples repository. In the repository, only a part of that, the provided component. Tool that works in a single administrative domain for very wide area networks. In those cases in which the propagation delays between the cluster of controllers and the network devices could be not negligible. And so we clusterize the network in order to be more responsive to network failures. And but also it is also designed to can be applied also for scenarios of multi-administrative domains. In fact, it is based on a peer-to-peer model, a hierarchical approach, so that you can easily push configuration policies for the communication between cluster or domains. That said, okay, so the architectural goals. We have a network that under a single or multiple authoritative domains, and we want to split the control plane of such networks into clusters. Then we feature such cluster with an east-west interface in order to enable the programmability of the entire network. On the slide, Icona is placed in the southbound of ONOS. I will say, I will spend a little bit more words later. And in order to provide such east-west interface. Then once provided this interface, Icona is in charge of sharing the local topology with the remote cluster in an aggregated form. Slide, you can see in this case, the local topology is abstracted as a single big switch, are used to connect customer edge points on one side and the interlinks on the other side. But actually this abstraction could be of other type depending on the use case application. For example, in the single authoritative domains, it could be maybe you want to apply engineering algorithms. So you want to may want to expose more details of your local topology. While in the multi-domain scenario, be fine because you hide the details of your network. Then I would like to point out that the customer edge points in these slides are IP router gateway, but actually depending on the use case could be other virtual machine, terminal host, sensor devices. It really depends on the use case and application. We share the topology. The next step is to offer the capability of traffic steering, inter-cluster traffic steering. To the application, a transparent end-to-end programmatic interface to the northbound applications. Actually, this is already provided by ONOS, this programmatic interface, through the flow rule subsystem, the flow objective subsystem, and the intent subsystems. But what we want to achieve is to also to expose the remote cluster network elements to the local network applications, northbound application, in a transparent way, and made it programmable end-to-end. So, as I said, Icona is an ONOS application, a framework application of ONOS, completely independent from the core system and from the other applications. And in order to achieve such transparency, to offer such transparencies to the application, and to satisfy flow rule requests coming from the northbound application, from the remote clusters, and to share the topology, you need to place Icona in the southbound. And in fact, we implemented Icona as a provider component. From the slide, it's clear, but once Icona has managed to share the topology, it notifies the core of the remote elements, and for the core point of view, as if it were the local elements, and seamlessly connected to the other devices. So as I said, the main component, logical component of Icona is a provider. And so looking a little bit more in the internals, we are trying to decouple the logic of Icona into the provider, so the topology and flow provisioning to the northbound application from the implemented mechanism used for the communication with the remote clusters. Because we do not want Icona to be tied to a single communication mechanism, but we would like to have the possibility to multiple mechanisms for different clusters at the same time. So I'm implementing the REST, a REST channel, end-to-end REST channel as a southbound mechanism for the communication. And another partner is extending the BGP to use it as merely as a track transport protocol, not for routing, in order to exchange the topology. Instead, I implemented a simple stateless REST communication for the moment. So instead, the provider component is logically divided into three components, three managers. The ones in charge of topology, receive the remote topology, and also to listen to local network events. And if something affects what it was previously exposed to the remote cluster, it is in charge to communicate some changes. Instead, if, for example, internal link failures, the connectivity among the clusters, this won't be communicated to the remote cluster. This way, you lower down the management of the network failures. We have the flow manager, which, as you can guess, is in charge of satisfying the flow rule requests coming from the northbound application and from the remote clusters. This is quite a delicate component. I have a slide dedicated for this. Then there is the policy manager, which enforces configuration policies for the communication both for topology and flow data. Is transversal to the other two managers. And this is especially important in the multi-domain scenarios. However, this component is still under study from our side. Once we will have consolidated the other two, we will put more effort on the provisioning of configuration policy. Even if we are already providing some form of policy when we decide to abstract the local topology as a big switch, and together with sub-destination to expose to the remotes. But this needs more study from our side. And then, as I said, there is the communication mechanism that are implementation of a common southbound interface in order to satisfy requests both for topology and flow exchange. Okay, then one last slide on the technical aspect. The flow manager, which is the objective of the flow manager. With an example, we want to transparently install and guarantee connectivity from located in two different clusters. So a network operator, an intent, a host-to-host intent with the two hosts located into different clusters. ONOS receives such request. With the intent subsystems, convert the request into batch of flow rules, each batch for a device along the path between the two hosts. And in the meantime, I Icona is a tool provider. Icona is a provider, remember, the multi-domain of the cluster device exposed by the remote cluster. So Icona intercepts the batch of flow rule dedicated to the virtual abstracted device. While the intent request is still in pending state, Icona sends a request of flow installation into the remote cluster. Icona receives the request and converts the remote request, the request of cluster A, into a local intent mapping between the connect point of the big switch into the egress point of cluster A network towards up to the connect point towards the host, and then install the batch of flow rules and send back an outcome to the cluster A, so that cluster A can change the intent request state from pending to installed or failed. Sometimes it fails. Okay, so this is, I think, this is the most interesting part of the project, to give a transparent view to the northbound application and to steer the traffic, inter-domain traffic. Okay, this is I will start the video now. This is the steps of the demonstration. So we have the two clusters as before. They expose the topology as a big switch, and then in cluster A is requested an host-to-host intent. You can intercept the flow rules, send to the other cluster, and then the two hosts are able to ping each other from the Mininet emulator. Let's see. Momento. Next time will be live, the demo. Oops. Okay. Sì, sì. This is the Mininet topology used for the demonstration. So we have three switches in one cluster, three switches in the other, two hosts and two hosts, and one interlink. So we have the GUI for the two clusters with three controller instances in each cluster, and also two CLI in each cluster. In each cluster, we have three nodes, three controllers. Okay, then now we activate our app. It's a simple app, OSGI ONOS app. So modular, and you can install and uninstall it. If you install it, then you have a state to maintain. In both the cluster, we install the apps, and then we launch some configuration for both the clusters, like the endpoint addresses for the communication. Plus, we disable the link discovery protocol among the two clusters, because you don't want to use the link discovery protocol between, for example, in a multi-domain scenario. Here we start the topology, the Mininet topology, as you saw in the slides. Okay, this is cluster one cluster. We don't have, with two hosts, we don't have the interlink yet, because there is no way to discover it. And this is the second cluster with two hosts. Okay, the same. I will. On the CLI, we see three switches, 6 links, unidirectional links, and two hosts. Issue a command from configuration. We instruct both clusters to share the local topology. This could be also asymmetrical, but I have done this for both the clusters, so both share their own topology. this command is simple. Is saying to the provider, okay, as we give to the provider a set of destination and build a big switch for a specific domain. And so we see this is this one, which is the aggregation of the other 3 devices of the other class. And we have also another bidirectional link with the information on the ports, virtual device. And the same is for the other cluster. So at this point, the topology has been shared in the form of the big switch, but there is no flow rule installation installed into the switches. No rule instructions. So here we see we have for the switches 8 links and 4 host devices. And now I think yes, in the mininet from mininet, one host is not able to reach an host in the other cluster, of course, because there are no rules installed. Then from a GUI, okay, 0 packet transmitted. Simply from a GUI, we select 2 hosts into different cluster, and we issue the host-to-host intent. And so it happens all the process described in the slide before, Flow Manager. And we see we have this intent issued by the GUI. So the application ID is the one of the GUI. Instead, in the other cluster, Icona issued the intent, 2 intent, point-to-point intent. So it has received the request and translated into an intent, local intent request. Here, I'm showing also that you can do the same thing with the command line. So you see the intent, the state of the intent. And that's it. I think if you have questions, we can also move forward to the question. Here, I'm launching another intent. And now we have 2 intent installed. And we have a guaranteed connectivity. That's it for the moment. The next step are the management of the interlink failures, because ONOS cannot handle interlink failures while it handles local link failures, part of the routing. And we have also to implement other defined APIs like the remotion of the intents before proceeding to the configuration system. Okay.
Thank you. And thank you.
Very
Basically,
fast.
1-2 minutes for a quick question. Maybe we can, otherwise we can handle them during the lunch break.
Yes,
we have quite
I'm
strict
going away.
rules
Yes,
on the...
there is also Michele Santuari, which is working with me. So for the later question, I mean, because I'm leaving in 10 minutes.
He's escaping, so it doesn't get any question.
Okay, hello. One quick question. What exactly is sent from one domain to another domain? What information? Is it just a list of endpoints where hosts are?
You mean for
topology information?
In which phase, the topology exchange process?
Yeah.
Yes, we are started with the abstraction of the big switch. So we simply send a list of hosts, MAC address. In this case, MAC address, so it's a general case, but MAC address are destination. Then the name of the big switch, the name of the device ID, and the ports where interlinks are attached to, together with the interlink ID, so that the remote cluster receives these ports, and from configuration can build the interlink. So it's very simple, the data, the transmitted data.
So
for the moment.
Because it looks similar like NSI, but NSI defining endpoints, you can define even unused ports.
Yes, but I think you can do it also in this case, but depends on what you want to. For me, I decided to share MAC addresses, and from MAC addresses you build the ports of the big switch. But you can also build the big switch with touch the host MAC addresses, and in other ports you leave that open for some further destination or other interlinks.
So it's basically very similar. You can define endpoints and propagate it to the different domain.
Yes.
Saying, okay, hello, I'm this domain, I have these endpoints, and
exactly.
establish a link to this.
Yes, now I have done this through configuration. I set the command to the provider and the command. The next step, from my point of view, is to automate this. So when a new host come up in the local topology, Icona should be able to check the policy, see if this host has to be communicated to the remote cluster, and do it without manually configure all the list of hosts. Okay, so we need more automation.
Is there intent to define endpoints from the GUI, for example?
I don't understand the question.
If you are in the ONOS GUI, can you define endpoints in your domain which will be propagated to the different domains?
I never think about this. So you mean from the GUI you decide you issue another endpoints?
If it will be from the GUI.
Okay, fact.
Can be list of.
Yeah, sure. We have to automate this process of communicating the endpoints.
Yeah,
yes. For the moment, there is a list given from configuration. Okay. Well, there are.
I'm sorry, since we have to rush to lunch according to what our hosts are saying. I will kindly ask the other questions to be done to Michele, to be addressed to Michele or to Francesco via email.
Yes.
We will have a second session in the afternoon. We will start with the latest presentation of this cooperation with ONOS universities, and then we'll go for the community discussion. This morning sessions.